Hey, welcome back to Math with Patrick. Today's January 14th, and we're solving the 14th problem from this Daily Epsilon calendar. Let's try it out. We have two natural numbers that differ by 4, and the sum of their squares is 106. Find their sum. Okay, so a natural number, I've defined it earlier in the series, but it's a number that's part of a set that starts at 1 and counts up by 1. And so essentially a natural number is a whole number, 1 or greater. Some people say that 0 belongs in here too. It's kind of contested whether or not you do or don't. I prefer just to say no. So a natural number is 1 or higher, and it has to be a whole number, 1 or higher. When they differ by 4, that just means their difference is 4. So like 8 and 4 differ by 4. And when it says the sum of their squares is 106, that means that I should try squaring both of these numbers and add them up because it's a sum and see if it matches 106. Now 8 times 8 is 64 and 4 times 4 is 16. So together this makes 80, which is a little bit too low. Doesn't really hit 106. So I know that 8 and 4 don't work. From this example, I know that I just need to bump up my numbers a little bit more, because if I make a number bigger, its square will be bigger. So 9 and 5 or 10 and 6 probably work, one of them. Knowing the answer is 14, I know now that 9 and 5 is the answer. But I just want to pretend that I'm not really quite sure, and maybe I'll solve this algebraically, and hopefully I'll get 9 and 5 in the end. So I'll call my two natural numbers a and b. And when it says that they differ by 4, I should be able to subtract them and get 4. And when it says the sum of their squares is 106, that means I should square the first one and square the second one and get 106. And now I have what's called a system of equations, or I have at least two different equations and some amount of variables. And in this particular system of equations, I could actually solve for both of them. Whenever you have the same amount of variables, so I have two, a and b, and the same number of equations, like 1 and 2, then you should be able to solve for them and know what their actual values are. So I'll do a little bit of work with this system and figure out, what are a and b? One of the most standard ways to solve a system of equations is to use a strategy called substitution. And to do this strategy, you first isolate one of your variables, or get it alone in one of the equations and stick it in the other one. That sticking into the other equation is called substitution because you're swapping out some values that are equal. I noticed from this first equation, this one's probably the easier one to isolate one of the variables. If I add b to both sides of the equation, I can rewrite it as a equals 4 plus b. And now I've isolated a. This lets me stick in a 4 plus b for this a right here. It's still squared, so I need to square 4 plus b. And this plus b squared is already still here from the second equation. All of this should still equal 106. Now I'll expand this one. I like to use area models for my polynomial multiplication. And so I have a 4 and a b and a 4 and a b, and it's squared. So 4 times 4 is 16. 4 times b, I'll just call 4b for now. Another 4b right here, and then a b squared goes there. So if I add up all of these small bits, it's the same thing as multiplying 4b times 4b. And I'll write it in standard form. That just means putting the highest degree term first, combining the two 4b's into an 8b. There's that 16, there's that b squared, and finally the 106. To combine my like terms, I have two of these b squareds. So I can just call that 2b squared, and I'll keep all the other terms the same. Well, now it looks like we're solving a quadratic equation. The first thing I'll do is just divide everything by 2. All of these are even numbers, so I could just divide both sides by 2 before I start worrying about how to solve quadratics. Let's see, 106 divided by 2 is 53. And what's best is to get it into standard form and specifically get it equal to 0. So when I subtract 53 from both sides, I'll just get whatever 8 minus 53 is right here, and it'll be equal to 0. That's going to be a 45. And hopefully I can factor these. Factoring is finding two things that are multiplied to get the same expression. And at least in this setup, the general idea is that I'm finding two numbers that multiply to negative 45 and add to 4. Looking through the factors of 45, I got, 45 and 1, then I have 15 and 3, 9 and 5, and then the next one would just be 5 and 9, which is that one again. So here are all the different pairs of numbers that multiply up to 45, and, one of them's got to be negative because they multiply to a negative 45. And I notice that if I take a 9 minus 5, then I get that 4 that I wanted in the middle. So this could be written as b plus 9 and then b minus 5. And now I'll use that zero product property. That just says that if I have something times something equals 0, well then surely one of those, maybe both, but at least one of those has to be a 0 to get a product that equals 0. So it could be like 7 times 0 is 0, 70 times 0 is still 0. So if I got two things right here multiplied that equals 0, well then either b plus 9 is 0 or b minus 5 is 0. So I get two potential solutions for b. Maybe b is negative 9 or maybe b is 5. So let's scroll back up a little bit because it says that these have to be natural numbers, which are again 1 or greater and whole numbers. So even though down here my math says that 9 or negative 9 is a solution, I can't accept it because it's not a natural number. So I know that b is 5 from all this hard work. And after this step of substitution and solving for one of the variables, I can go back up, pick an equation, and plug in 5 to figure out what a is. This first one is a little bit easier to use, so I'll just say a minus 5 equals 4. And then it's pretty clear to see that this a has to be a 9 because 9 minus 5 is 4. Well, just to make sure that this all works, I kind of knew it was 9 and 5 from the start. I can take 9 squared plus 5 squared and see if it gets 106. 9 times 9 is 81, and 5 times 5 is 25. And then the 80 and the 20 make a 100. The 1 and the 5 make a 6. So yes, indeed, the squares, or the sum of the squares here, does make 106. Got it. Well, what's the sum of 9 and 5? That is 14. Sweet. We did it. We found those numbers, and that's the end of the video. Thanks for coming along with this journey, solving this problem with me, and I'll see you in the next one. Bye. After all of that, I just realized that my notation was wrong somewhere. The natural numbers is the set equals the set 1, 2, 3, 4, 5, and so on. Rather, a and b, the numbers that I found, 9 and 5, those are elements of the set 1, 2, 3, 4, 5, and so on. Oh well. Found that little mistake in the end. It's just a little notation thing. But I saw that after the video and I was like, silly me. It was there the whole time. Oh well. I just wanted to clear that up and close my set right there. Whew. Okay. Notation aside, all the math still makes sense. So, alright. For realsies by this time.